Hello guys, so today is the day 3 of deep learning. Basically, in the previous lectures of deep learning, day 1 and day 2, we have covered the ANN architecture and how basically input will looks like and how we have to pass the input to our ANN model and what is the corresponding output looks like. And basically, we have done some optimizers also if there is a problems in some optimizers what we say in softmax function, then we have to apply a different activation function. Basically the first activation function is basically softmax, so there is some problems in softmax, so we have to apply another activation function like sigmoid, and other activation function are relu, leaky relu, pre relu, and adam not its optimizer activation function is basically Swiss activation function is also there. So in all of these activation function, the relu activation function works better because it reduces your uh, overcome your vanishing gradient problem, which was held in RNN and our deep neural network. So basically, we will use a ReLU activity function. But in this optimizer, also there is some problem like dead neuron problem. So to overcome this neuron problem, we will have our next optimizer activation function, which is called leaky ReLU. The formula is basically max of 0.001x comma x, which will solve both of the problems. Now coming today, we also to the previous lecture I have covered the loss function also, like this is different types of loss function what do we say, gradient descent. For gradient descent, for binary we have binary cross entropy, and other like MAE, MSE, and other the activation like loss functions are there. Let's see it. So where is this complete deep learning? Uh, so we have covered this ANN and vanishing due to vanishing gradient problem because of chain rule or differentiation. The vanishing gradient problem occur in sigmoid. So we have a 10H activation function. Also also we have seen like how this we say prone to vanishing binary classification suitable clear prediction. 10H will solve also like zero centered problem also, but it has a vanishing gradient problem, and time complexity is very like it has, so that's why we don't have to use 10H. The ReLU activation function, like 99% we will use our ReLU activation function in between of our model. And now we have covered all of these functions like leaky relu, elu x, the if the value of x is greater than 0, and alpha into alpha basically is there or hyperparameter into e raised to the power x minus 1 otherwise. So which will looks like it's a zero centered also, slightly more computational. Yes, but it is the best, but we are using a relu because its time complexity is very low. That's why. And that's it for loss function and cost function. We have already seen that basically loss is for 1 point and cost is for the summation of all the losses you have. Mean squared error, we have seen that. We have then MSC, RMSC, and loss for binary. Basically, we have binary cross entropy, categorical cross entropy, and sparse categorical cross entropy. Okay. So binary we have already seen that this formula is minus by log by minus 1 minus by into log of 1 minus by basically. Categorical cross entropy is for multi-class classification. This is the softmax activation function is basically e raised to the power zi upon summation of e raised to the power zj. Sparse categorical cross entropy, right combination. We have already seen if you are solving a problem related to binary class classification, Then in output layer we have to apply a sigmoid activation function, and between here we have to apply a ReLU activation function, or it's very like leaky ReLU, E-loop, ReLU you can apply. And if you are solving a multi-class classification, then in output layer we have to use a softmax activation function, and between we can use ReLU, pre-ReLU, something like that, leaky ReLU. If you are using solving a problem related to regression, then we can use a linear as a output layer, and really this in between we have to always use a ReLU activation function most of the time. And loss is binary cross entropy, categorical cross entropy, or sparse categorical cross entropy. In multi classes we can use. And for regression we have RMSE, MSE, Huber loss, Hinge loss. This type of losses are there. Now today is the day 3, and now comes to our main agenda. Today we are basically covering the optimizers. Basically we have different types of optimizers, and in all of these optimizers, Adam optimizers is the best optimizers, and 99% we will use this optimizers. Basically the optimizers is used to update the weights of our model. Basically according to this loss function, we are using if we are using a loss function like this, uh, suppose RMC, and we have to use this losses. So like which optimizers we have to use so that our bit updation will be happen in the right way. So the first optimizers the scientists have discovered is gradient descent. Gradient descent, I think you have learned in the linear regression. Basically this is the basic optimizers. But in every algorithm we have to use it, this gradient descent function. So there is some problems in this gradient descent, so that's why we have to learn like SGD, mini SGD, SGD with momentum, AdaGrad, RMS props, and Adam optimizers. We will learn like what are the problems so that we have to use this one, and what is the like advantages and disadvantages of this and this, and like why Adam optimizes the best now. Now today Adam optimizers is the best optimizers, but in future we can see that another variant of this optimizers basically. So now I'll start gradient descent optimizer. So we already know that gradient descent uses a loss function of RMSE. Basically it's not RMSE, it's MSE, mean squared error. So the loss function will looks like summation of pi minus pi I ka whole square. So the formula to update the weight is basically W equal to W minus neta into differentiation of loss function with respect to W. So which looks like this. A gradient descent formula like curve will looks like a U curve. So this is the global. Our aim to find this minimum value. So if we are using a small program, then we can use it like a small problem like related to linear regression, binary classification. If your output does not have any outliers, or if your problem is very simple, then you can use it as a gradient descent. So this is the loss function we have landed now. So what is the problem in gradient descent basically? So what in gradient descent basically we will suppose we have to train our model for 100 epochs. If your data set has million of records, then what happen in gradient descent? This gradient descent will pass all these million records at a time, and then calculate the error corresponding to this all of the record. And so what happened, like suppose you don't have a this much of GPU, and suppose your RAM requirement is also the problems. Like basically hardware requirement here is very like we can say a problem, because hardware nowadays is very high, but in future it will be now decreasing somewhat. But this is the problem, like in this gradient descent if we are using a gradient descent optimizer, so in that basically we pass all this record at a time, and then pass this loss function, and then update our weights according to this formula of gradient descent. So convergence will happen very fast in this. If you are using this optimizer, convergence will happen. But disadvantage, huge resource like RAM, CPU, GPUs. You want more because the computational power is taken very high in that case. Because you have to calculate all of this bit at a time. It's like in 1 million record you have to calculate at a time. This. So it's basically disadvantages. This only like resource intensive. It is. So now we have a second. The scientists have like discovered a second gradient descent version. Like they name given as stochastic gradient descent. So the difference between this like gradient descent and stochastic gradient descent is only this. In stochastic gradient descent, we will pass one record at a time. So suppose your data set has a 1 million record, then in every epoch you have to iterate 1 million times. So this is now again a problem. So researchers have found like the convergence will happen, but it will take huge time. Like for every like suppose if you were training 100 epochs and your data set has a million record, then it will take 100 million iterations. So this will be a very like time complexity or very huge problem related to time basically. Advantages: solve resource intensive. Like now you don't want any like high requirements of hardware like CPU, GPU like this. But the disadvantages in this like it is a time complexity, and convergence will also take some more time. Like in one epoch you will passing a like one times record, and so convergence also will be take more times and noise gets introduced. Like so every points you have for one point you have calculated a error, and according to this error you have updated this bits in one epoch and web propagate this model so that updation will be happen. So due to this the noise will be very high. Like your model is giving this much of basically we say error, and this same error will be like every time but you are passing every one record and calculating the error, so every time the error will be high basically. So this also noise gets introduced in this model. So now researchers will did not quite like they have to find another way so they can get a good accuracy. So they have found a third variant of gradient descent. They have given a name as a mini batch SGD. Now SGD is perfect basically, but it has also some problems. So they have like introduced another optimizers so that we can get a good accuracy. So in that basically in one epoch at the time of training our model we have to pass like what is our batch size. So basically we will pass a batch size of 32 in most of the times. So now the problems will be solved. Like here the time complexity is also not a problem now, and the resource intensive it is not a now problem. Like if your data set is a 1 million record, then we have to pass like a batch size of 1,000, then it will take 100 iterations. So it is not now a problem. Like you can train your model like in 8 GB or 16 GB of RAM, you can train it. So now the mini batch SGD, so in that like advantage, like convergence speed will increase in respect to basically SGD, stochastic gradient descent. Noise will be less than compared to SGD. Yeah. So basically at a time we are passing some batch size, so the noise will also be reduced respect to SGD. Effective resource usage RAM. Like now it's using also a RAM size in an efficient manner. Now, what is the disadvantage? Noise still exists. Like here we can see still we have some noise. So this is again a problem, like we have a noise in our data set. So the researchers will not keep quiet again. They will now find another function which they have now name given as a SGD with momentum. So what is in this momentum will happen. So basically in momentum, I think you have learned the about basically time series problem. So if you don't know, then I think you can't understand. If you have learned like how time series will work, then I think you are able to understand it. So in basically time series data set, we will create some smoothing. There's some smoothing factors there. So we will some, if your data set have some noises there in your data set. So by introducing a smoothing factor, basically we will now able to reduce this noise. So scientists have received basically introduce SGD with momentum, new approach in optimizers. So the like moment noise is get reduced with respect to mini batch SGD. So now it has, but it still has some noise, but it can be possible. Like it can, we can take it as a noise. We can take it, this model. So the formula will be W equal W. This is the net as the learning rate. Mm. So smoothing line, like if your data set has something like a red color line, something like that, by introducing a smoothing, we will get some smoothing line. So which will be able to solve our problem. Like in Arima, we can say that Arima model, Arimax in a time series, we will have this. So by basically we will give in the formula of smoothing is basically v of, well, like the value of at time 2 is equal to beta into v of t1 plus 1 minus beta into a2. So beta is basically a hyperparameter. You have to change it at the time of training. Basically the time of training it will be update also, we can say that. And vt1 is basically value of time this time. So what percentage of basically we say value you want to give to value at this time, and what percentage of this, like opposite to the beta minus beta, like the summation of beta and plus beta minus beta is equal to 1. So if you give 95% or we can say of 10% to value of t1, then automatically 90% of the weight is given to your previous output of your model. That's how basically we will introduce a smoothing in the SGD with momentum. So basically, we will apply this SG like a momentum in our beta updation formula. So our beta updation will be also have some smoothing factor. Previously, it's going something like dig 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 dig, but now it will be something like ding 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 ding. So it will be now, so noise will be get reduced somewhat, but still have a some noise. So now advantages: reduce the noise, quick convergence. Also, like it is same as mini batch, but here we have introduced like smoothing factor in our beta updation. So our beta updation will be happened in a good manner. So it's a quick convergence as mini batch SGD. Also, it's reduce the noise which was held in mini batch SGD. Now, the scientists have now never quite, they again find a new variant of gradient descent. They have given now a ADA name, adaptive gradient descent. Adaptive gradient descent. So in that basically they have introduced basically uh, we can say a smoothing factor, or no, in that basically they have introduced some basically our learning rate previously is fixed. Like suppose at the time of training, if you fix your learning rate is 0.01 or something like that, then it will be fixed. So now suppose if at the starting you are there, suppose you don't know anything, then if you don't know anything, your error will be high. So you have to learn in a very fast manner. But after some time, suppose you know many more things, after here you are, and it is the 100% of your knowledge, but here you are. So now you have to learn in a slowly manner, so that you can get a this point. If you learn very fast, then maybe you can get this point or this point, like something like dot will happen. That's why here you have to learn very fast so that you can get this point. And if you are coming to this nearer point, then your learning will be slowly. So that's why the researchers have never keep quiet. They have find another variant, or they have never name given as adagrad. So in that basically our learning rate will be now neta by under root of alpha plus neta. Neta is basically your epsilon value. So why up in your mind will come like what is epsilon? Why is epsilon is coming? Alpha t is basically a differentiation of your loss function basically alpha of t, alpha t. So neta dash is equal to neta like learning rate upon alpha t plus epsilon. Neta is your learning rate, and basically we are dividing the learning rate by alpha t. Alpha t is basically differentiation of your loss function with respect to w. So like differentiation of loss function with respect to w, it's if you are coming this like near to your global minima, this will be also will be decreasing every time. So due to this, your neta value will also be decreasing if you are coming to this point. So why epsilon? Suppose your model will be overfitted and your loss function will be zero at a time. Suppose you have a data set or a model that will be overfitted. So at the time of overfitting, your loss function will approx to zero. So the value of this under root will be approx to zero. So 1 upon 0 will be infinite. So that's why we have to introduce some epsilon. So even if your loss function will be 0, you will not get a infinite, like your function will not get a infinite or will not get a stuck in a infinite loop. So that's why we have introduced this epsilon. So the formula is neta is equal to neta like our learning rate upon under root of alpha t plus epsilon. Alpha t is basically the differentiation of your loss function with respect to w, and plus epsilon is there. So that's it, and it's like so that's it. So for neta, possibility to become a very small value approx to equal to zero. So yeah, so if you like every time if you divide this value like your learning rate and neta also a small value, if you divide every time this will be approximate like every time if you divide this value, your value will be every time will be reduces according to your loss function. So maybe it's possible to approx zero. So your updation of bit will be not happening. Your updation will be happen if your error will be high, and if your error will be slowly like very low, then your updation will be also very slowly. So now this is again a problem. So the researchers never keep quiet. Now they again introduce a new variant of your optimizers like ADA delta and RMS props. We can basically we can say that ADA delta. Here we have learned like ADA adaptive gradient descent, and adaptive gradient descent. Adaptive means basically we are adapting your learning rate. ADA delta. So basically in ADA delta, our bit updation formula will be something like that. So here now we will introduce smoothing in weight and learning rate also. Not learning rate. Basically in Adam optimizer we have to introduce all of these things. So here our like built like this learning rate will have introduced a basically a exponential factor, basically we can say that, so that we will get a exponential bit average. So in ADA delta basically or RMS props, basically we can say RMS props, our learning rate will be basically we have learned this like what is the disadvantage and advantage with respect to gradient descent, SGD, minimatch SGD with momentum, and ADA. In ADA, basically we introduce a learning rate with learning rate equal to learning rate divided by under root of alpha t plus epsilon. Alpha t is basically your error. So in basically at a delta, there is some problem like possibility to become a value very small zero. So in at a delta, basically we introduce a, basically we can say a momentum in the alpha t. Alpha t like in your learning rate, like your learning rate now become will be neta by under root of s of del dt dw plus epsilon. Epsilon is same here also, but here we have introduced a smoothing factor in the our alpha t. Alpha t is basically your error is equal to summation of by minus like differentiation of loss with respect to w. So in that basically we have apply basically smoothing factor so that our bit updation will be happen in a good way. Now the last optimizer, and which is the good optimizer like Adam optimizer, you have to learn this. This is the best optimizer, and every algorithm like 99% we will use this. If you are using ANN, CNN, RNN, any problem like transformer, BERT, chat GPT, everywhere we will use this Adam optimizer as a loss function optimizer. So in Adam, basically SGD with momentum plus RMS props, dynamic learning rate plus smoothing, all of these things will be combined inside the Adam optimizer. So your formula will be now basically we can say W nu equal to W volt is there minus neta. So in neta basically we have introduced neta by neta dash equal to neta upon under root of alpha t plus epsilon is there, but in Adam basically alpha t we will have some smoothing factor. So the smoothing factor now will become basically s of d, basically s of w of s of d of w. S means smoothing factor, differentiation of with respect to weight. And in also basically in this also there like differentiation of loss with respect to w. So in v also we have introduced some like momentum, so this will looks like vdwt equal to beta. Beta is basically your hyperparameter. It's also hyperparameter in your alpha, like your alpha, like in your learning rate, alpha t basically. Here also we have to introduce some your hyperparameter basically. So that's it for Adam Optimizer. Basically, Adam Optimizer is the combination of SGD with momentum RMS props. RMS props is basically dynamic learning rate plus smoothing is also there. Smoothing is apply in both of these optimizers. Basically, we have learned gradient, SGD, mini batch, SGD with momentum, ADA grad, Adam Optimizer. We have already seen this. I don't know why this is coming again. Basically, we have covered all of these. Which Adam optimized. Yeah, it's done. Like now, coming to exploding gradient problem. Bit initialization techniques. Or we can see it in the next lecture if we want. Dropout layer, see, and convolution neural network. Okay, so today we will learn about this dropout layer. Yeah, today we will cover on this. CNN will be covered in next lecture. Now, Adam optimizer is done. So, exploding gradient problems. What is exploding gradient problem? Suppose you have taken your learning rate as a very very high number, and your loss will be very high. Then the bait updation will be very very high. Your gradient descent formula like curve will be jumping like this dum 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 dum. You will never get your local minima. So this problem is known as exploding gradient problem. Like you have big number and big, like due to chain level of differentiation, we are scoring our uh, basically our loss function. So every time you are getting a big number. That's why this problem is known as exploding gradient problem. Your value is from 0 to 25, but you have multiplied in a big number, then you will get a big number. Bit initialization very high value. That's Now coming to base initialization techniques. So bit initialization techniques for ingredient numbers. Yes. So we have three types of initialization technique in the deep learning. So first one is uniform distribution, or the second one is JBR or Gilroy initialization. The third one is Keming he initialization. Keep on. Base should be small. Weights should not be same. Weights should have good variance. So these are some advantages of this. Like in uniform distribution, basically weights should be small. Basically you have learned a uniform distribution curve, basically a bell curve, so in that bit should be very small. And the second one is JVR or Galorot initialization. Galorot, basically in that bit should not be same. Basically different types of bits are there. So in uniform distribution we have a formula like this: Wij equal to uniform distribution like minus 1 upon under root of input comma 1 upon under root of input. So if your input value is a 3, then it's become minus 1 by root 3 comma 1 by root 3. So this is a uniform distribution. Uniform basically is create a bell curve. The second is Javier Clorot initialization. It is basically researchers Javier Clorot. It's a name of a researchers who have researched this given a name. JVL like normal initialization and JVL uniform. There are two types of initialization technique inside a JVL. So if you are using a JVL normal initialization, then the formula will looks like W of ij is approximately equal to normal distribution of 0 comma sigma, and sigma is equal to under root of 2 upon input plus output. It's the formula. You have to remember this. Basically this is the initialization technique. They nobody will ask you, but we have to know this. And if you have a uniform, this then will be minus under root of 6 upon input plus output, just like this. In normal, basically we will take 2 upon under root of input plus output, but in uniform we will take as a minus 6 upon input plus output. Now K-Ming or he initialization, this is the best initialization technique. Like most of the algorithm use this type of initialization. If you are using a he normal, then it will be a 2 upon under root of input, under root of 2 upon input. And if you are using a uniform distribution, then it will be minus 6 upon under root of input. This the he initialization technique is most of the time we will use. 6 upon input plus output 6 or 2. You have to remember this number. In uniform normal we will use a 2, and but in uniform we will use a 6 basically. So these are the some techniques. And dropout layer. So what will this, but the meaning of dropout layer basically. So at the time of creation of model, there's some function like inside a keyless dot dropout layer is there. So if you apply a dropout layer, and inside this dropout, you have to say to this model like how many percentage of layers you want to drop out from this layer in L1 layer, suppose. So if you apply a 50%, then like if you apply a 0.5, then 50% like your layers will be drop out, like half of the, like you can say a draw, basically a dead neuron. You can also say that like the connection will be closed, or the input output will not be giving in that way. This will be required if your model will be overfitted or not training very well. So at the time of overfitting, this will be required. And basically it's P, basically your hyperparameter. Feature sampling, row sampling, random forest, overfitting, generalized model, decision tree. Also, like in deep learning, if your model is overfitted, we have to apply we say dropout layer, or we have to basically many hyperparameters are there. You have to change it like activation function, optimizers. You can change it. Or in decision tree, if you have overfitting, then basically we apply some. in simple technique, or also we can prune this tree like before growing. These are some techniques which sampling. If you test data, this is it for the dropout. I think I have explained in a good way. Thank you guys. Jai Hind, Jai Bharat. We will meet in tomorrow's lecture. Let's see what is CNN. CNN is basically my favorite things. I love CNN. Basically, I love images, to play with images and all of this. Let's see the CNN in the next lecture. Thank you guys. Bye bye. Love you guys. Please subscribe my channel to motivate me to create like this content. Now I am only explaining these things, but in upcoming lectures I will be explain in a basic like from starting from linear regression and everything. I will explain you from basics. Like I will take 1 to 2 hours to explain every algorithm. Now we will taking a overview like how this will work and all of this like deep learning. After completing this deep learning playlist, I think tomorrow I will complete it. After completing this CNN, we will take some NLP related tasks, also learn NLP, and then after completing the NLP, I will start from initial, from basics to advanced. Everything we will learn it. Thank you guys. जय हिंद जय भारत. मिलते हैं दूसरे नेक्स्ट लेक्चर में.